Welcome to Destruction VFX Techniques with Houdini and Unreal. In this masterclass, I will demo two different techniques for employing shattered geometry from Houdini to use in Unreal. The first technique will utilize a mesh array of FBX files with the corresponding point cache data file to be driven dynamically with Niagara particles. The second technique will utilize a single shattered FBX file from Houdini that will be converted in Unreal into a geo collection and simulated with chaos dynamics. Finally, I will demo how a chaos destruction simulation can incorporate Niagara particles in a procedural manner to add extra dust and debris to the overall look of the simulation. For this first technique, let's open the Houdini file inside the Houdini project directory named fx_shatter meshes that is located inside the source art directory. Okay, looking at our Houdini file here, we're going to look at our geometry shatter statue 01 object and go inside, and we'll take a quick look at our SOP chain we have set up here. And this is going to be where we're going to take an existing game asset, this statue, and bring it into Houdini to bust it into pieces we can write back out as FBX. So we're going to read this in and look at the size of this, which is in game units, centimeters. It's too big for what we want to use, so we'll scale that down by a factor of 100. This will be more useful now for what we want to do in Houdini and the values we're going to want to use. Putting down our RBD material fracture, we're going to use a basic concrete fracture, just one level of fracture. 7 scatter points, not too many here, but we're going to change the distribution of the noise frequency. So it's going to be more stretched in the Y direction here, and the goal is that we'll have a different distribution of scatter points stretched out more along the Y. Then what I like to do is separate. I want the upper and the lower to be two separate elements, so I'm going to use a blast and the name attribute here, and in that way I can pick the upper pieces, branch them off from the lower pieces, and I'll go ahead and use those upper pieces to do some further shattering. This is also a place where I'll use a reference copy, and this is useful again to keep a procedural workflow where whatever I change on the blast of one will be reflected on the other. And this is now where I'll go in and continue to shatter those upper pieces. Again, a concrete shatter, just one level of fracture, but a little more even distribution of those scatter points. I can then merge the top and the bottom elements together, and then I'll use a null to end that termination point, give it a name. And I typically write this out as well, so I offload that out of our Houdini session. I'll often use a project, almost always, and in that I'll use those variables for $job and $hip name to help organize, and then an op name as well. Color by random attribute for primitive using the name attribute allows us to preview those pieces easily. And then I often can see as I do changes what those results are with the color SOP. After writing out and reading back in the shattered geometry, I'll triangulate it with a divide. That helps for any new faces. And then I'll use labs inside face UVs. And this will give me UV attributes on those newly created inside faces. I'll throw a normal SOP down as well for good measure. And then I need to create an attribute for the inside group of a shot material path with a name that I've decided, a string primitive attribute with the name that I've decided to call mi_inside. This will be important in order to give us another socket on our FBX geometry when we import it into Unreal. That'll allow us to have a different material instance on the inside faces while still using the material instance that came with the actual asset on the outside faces. I often use the exploded view then. This helps us to preview those inside UVs. Also just the shapes. If we have any really small pieces, we could easily see them here. And then I'll often use, again, a color sop primitive, and just for the inside and outside to isolate and look at very easily that way. After the assignment of the material inside attribute, I'll make these pack primitives. And then our next and final steps are going to be creating a point cache cloud of those pack primitives and writing out the FBXs individually. We're going to scale this geometry back up by 100, so it'll be written out as FBXs in centimeters now for Unreal. And then we have a for each loop here. So I like to start this process with the null. Again, I'll just have that as a pointer, call that in. And then in this for each, I'll create a metadata node as well, and we'll use that as our counter for iterations. Once in the loop, each piece is going to be sampled and processed. We will then assign this attribute for what I'll call an iteration attribute or an ID. And this will be a point integer attribute that'll look at, for each piece, each part of the loop we go through, the detail attribute of our metadata node. And that iteration value will be used and assigned to each piece in the loop. In this way, we'll use that to help when we're creating the name for each of these FBXs that we write out at the end of this loop, or at the end of this for each loop. Next, I want to go ahead and put all these pieces at origin. So I zero out their position to 0, 0, 0. This will be useful when we're assigning them in Unreal to our Niagara particles. And then I'll use another null, again as a placeholder pointer. And then we'll go and use a Python sop to actually do the execution of pressing the button using a who_parm function of our FBX output ROP. And how that'll work is I usually like to make this, again, procedural by giving a spare channel attribute, a spare channel that we can point to. And in that way, that'll be the name of that output driver. And in that fashion, then we are going to use that to press the button, which is a save to disk button. So each time we loop through this, we will write save to disk that particular FBX. Here we'll use also the in null to look at the number of points in our pack primitives and use that as our range. So the endpoints function looks at the in null and subtracts 1, so we have our range from 0 to that number, -1. Also, again, in the output file, I'll use a point function looking back at the incremental null, and the ID number there on each piece, each FBX pack prim, will be used as a digit in naming each of these, what I'll call SM underscore shattered statue 01, whatever digit it is, .fbx. So this will be useful no matter how many pieces I shatter. This workflow will stay procedural and flexible. That's writing out the FBXs. Now we'll back up a little in our chain to where we created the pack primitives. and then look at writing out a point cache of those. So from our pack primitives, we can go ahead and delete the actual primitive element with a delete SOP, delete all by pattern asterisk, but we keep points, checkbox at the bottom, and then we'll use a labs Niagara ROP to write this out as a point cache JSON file. And again, I like to use the project directory variables and op name to help again build this out in a procedural way. Now we'll jump into our Unreal project where I've already created some maps to work in and directories for our various assets to keep everything organized. So in meshes we have other directories for the different assets we want to bring in, as well as our point caches. And we can double check under plugins that we have, type up Houd. We have our Houdini Niagara plugin enabled, which we need in order to use point caches with our Niagara particles. So make sure that's checked on. And then we'll go back to our directory setup for the Roman statue A. That was the one we smashed in Houdini. So we have our materials already in place. We can right click and go to import. In source art under our effects project, we have that statue directory, and inside we'll see we have our 42 FBX files of those shattered pieces. We'll use the default FBX import settings. We want to import normals, and also we're going to change the default to not create a material since we already have this MI inside material instance and the Roman statue material instance. We say import all, and then we can see that we have all 42 imported. Double click on one and look at this in this static mesh view, and we can see that we have both the material for the inside assigned and the default material that was originally created for this static mesh. And that's looking good. So each of these have those materials auto-assigned because they're in the same directory. We can select all these FBX files and save. Next, we're going to go over to the point caches directory, and we'll go ahead and import that point cache data. Same idea, right click to import, and in the same directory where we wrote out our FBX will be our JSON file for the point cache data. If we double click on that, we can see the data in this file. We'll see number of samples. That's our 42 points for the 42 pieces, as well as a number of attributes like position and ID. And that'll be all we really need. So next, let's create our Niagara system to use these point cache and FBX files as a mesh array. And we've set this up already in our systems directory. So we'll look at that next. We're now going to build our Niagara system from the ground up with the point cache and FBX assets we just imported. Let's go Niagara system and choose empty for our emitter and say create. And then I like to give the NS prefix, and we'll go underscore, just call this Roman statue A. Underscore point cache is fine. I'm going to double click to open that system up. And we can see we have our empty emitter, so let's go ahead and rename that as well. And this is going to be a CPU emitter because we need access to the point cache data, and GPU won't allow for that. First thing we'll want is a user parameter, So we can bring up the plus arrow and type Houdini, and we'll see Houdini point cache info. That is going to allow us to use our point cache that we just imported. We'll select that and click on our arrow, and that'll be our point cache info parameter data. Now we're going to need modules for point caches on the emitter, and we'll start with our emitter spawn. Hit the plus arrow, and with the show all filtering, we can type Houdini, and we'll see our point cache module there, the init Houdini point cache. Go to emitter update. Again, click on our plus, and type up Houd, and we'll see the spawn particles. Here it wants us to point to the data of the Houdini point cache info. We'll drag that over. Under particle spawn, hit the plus arrow, and again, Houd for sample spawn under initialized particle. We're not going to need anything for particle update for our point cache. Okay, so now we have our point cache data set up properly. We're going to now look at creating the system to spawn these particles using that point cache positional data. And one of the things we're going to need is some additional parameters. So we'll go over to parameters under particle attributes, and we can see these that we got from Houdini here. We're also going to want to set parameters. So what we can do under particle spawn is set new, and in that we'll go and click on the plus arrow, the plus symbol, type up particle, and we want position. So we're going to change the particle position to be the Houdini position. So we can drag that. And now the point cache will dictate the particle position. We're also going to set the lifetime of our particles in this fashion. We can just drag that over from our parameters and drag it down in the stack. And the default life of 5 is fine. And now we're going to need to create a parameter that's an integer, and we'll name that mesh index. And that we're going to also set, drag it over to our particle spawn, put it in that stack. This is going to be reading the Houdini normalized ID. So we can drag that parameter over. And this will allow us to index the particle ID out of Houdini of our point cache with our FBX. Now with the default sprite render, we can see if we play on our timeline that these point cache particles are representing that point cloud we wrote out of Houdini. And that's why I'll use a sprite render just as a sanity check to look at the actual positions of these point cache particles. So ultimately we want the mesh render. So go ahead and hit the arrow button on render, or the plus button, and we'll bring up the mesh render module. And we're not going to use our default nomen. Instead, we're going to create a mesh array or a mesh flipbook. And we can enable that under the meshes. Right. In that section there, we'll hit the checkbox. The pop-up confirms we want to enable this flipbook. And we say yes. And now we go and point to the first FBX file of that array. Going back to our meshes directory where we imported them, we can see that we have our statue 0 static mesh. That's our first one in the array of 42. So we'll select it and choose our arrow key there. Then we're going to also need to change the number of flipbook frames to match the number we have imported, which was 42. And then the digits is fine. We only have a single digit in our name. So with that, we can see it populated the remaining 41 meshes. So we have 0 to 41 now as an array of meshes for our point cache particles to be associated with. And when we play this now, we'll see our statue's been reformed. 42 mesh pieces and 42 point cache particles together. So we're going to want to apply the forces, some dynamics. So we'll start with solve forces and velocity module under the particle update. And we can apply our gravity force. That's pretty bare bones, so that we'll have something pulling down on these pieces now. And then let's go ahead and put a collision module there as well. This is going to need to be right above the solve forces and velocity module. And we'll change these default settings so it's not a sprite type, but it'll be a mesh. And then I like to reduce the amount of bounce or restitution, bring that down to something smaller than the default. I'll also increase the particle radius scale. This all depends on what size your pieces are. And then I typically have a random collision normal, and then I like to check the control roll on collision. And then I typically have to make this radius scale for rotation larger than 1. And so now we'll just see that we've got some gravity pulling our pieces down. We can display the floor under our preview scene settings. And this is not that accurate in the Niagara viewport to evaluate, but it's fine just to get started. So let's go ahead now and look at adding some forces beyond just gravity. And I like to do that in the particle spawn section by adding velocity. And so this will be added only during the initial burst or the initial birth of our particles, not every frame. And I like that control. So by default, the linear velocity, I don't really need to use that. In this case, I prefer to use it from point, and that'll give me more control in a way with the origin offset that I can change. The velocity speed is your amount you want to impart, and usually it needs to be a fairly large number to see anything. So 300 here gets us a little bit of these pieces tossing, and then our gravity takes control to bring them down onto the ground. And we can then add offset. The origin offset will be a direction in a way for where these velocity vectors will be aligned or pointed. So I typically want to do a little variation so the speed isn't constant for all the pieces. I can have a random range float, and that'll give me a minimum and a maximum value now. Somewhere between 350 and 750 will be applied. And then I'll do a directional change here. So in negative 300 on X and negative 170 on Z, I'll have a directional along the X-axis and upward from the Z. So because we're negative, imagine the direction they will fly is the opposite of that. And so these values you can play around with and modify depending on what your need is, but I typically like to have these exposed as well as a parameter that will then be available on the details panel of the Niagara system. in a level. So let's go ahead and make some more user parameters. We'll click on our plus button, and what we want is a float, and it's going to be for our velocity speed. So we'll make a float that'll be the max vel, and we can give it that value we liked of 750. And we can make another float that'll be our min vel, and this can be that value of 350. Then to apply these, we'll just again drag them over onto the parameter we want them to be used. And then let's do the same for our origin offset. In this case, we'll need it to be a vector. And again, we'll give it an appropriate name and type in the values like we have set already as a default. And by having these values as the default in the parameter as we create this system, those will be saved and used as the default values anytime you use the system. And drag that over. And then let's take a look at this system now on the level. So we'll browse to that, drag the Niagara system onto our level, and we can see it's auto-activated and is looping. But we'll be able to modify these parameters here for our instance of this Niagara system in the level. And each one can be distinctly different if we drag more or copied more of these Niagara systems. We can modify these parameters individually. These parameters will also be exposed if we chose to use a system in a sequencer, and that's another advantage of exposing, making these parameters and having them available or exposed at this level. We can also point to the different point cache if we need to change that as well. All right, so back looking at our system and the emitter, we're going to get into our particle update and add a little bit of drag. This is something, again, based on the behavior I want to achieve. I'll play around with the amounts of drag affecting those particles. And this is something, again, I just iterate on and find a value that works. Typically, I always want to have my pieces rotating when they're flying through the air. So to do that, I'll go ahead and create under our particle update a mesh rotational force. And in this way, we'll give a little torque, a little spin to our pieces, and they won't feel stiff or linear when they're traveling through the air. And the way the defaults are set up is to align rotation of force by the simulation space. But I like to mix it up by having a random range vector give a negative value for the minimum and a positive value for the maximum. And that'll allow for a clockwise or counterclockwise rotation. And then I'll multiply each of those vectors by a float, so that would be the amount of that rotation, that force. Whereas the vector values -1 or +1 is more which direction, clockwise or counterclockwise, would it travel. So you can play with the numbers here, and something crazy like 45 will be too strong, but you get an idea that this is something that gives a lot more realism if these pieces are rotating as they're flying through the air. So we'll dial that number down to, say, 8. And this would be another good example of creating this as a parameter that would be a float parameter for the amplification, the float value that's multiplying those vectors. So we'll call that rotation amp. And we can use this one float for both of those uses, for the minimum and the maximum. Or if you feel a need, you can make them separate if you want different control values that way. So here again, now we can evaluate the system in the level, and we can determine, based on the behavior and the scale we're seeing it at, if we want to modify those settings. Now let's go into another system I've already built, and we're going to add to our point cache mesh array of the shattering some additional elements that will be some small extra debris and some dust elements that are sprites. So these emitters are already built out and running with the same emitter for the point cache of our shattered statue. And all systems tend to be a collection of multiple emitters to get that look. So if we turn off the render of our point cache, we can just see the extra debris being flung out. And this is a system, or rather this is an emitter that is just creating a basic shape, sphere shape that's oblong, and setting the same types of velocity, rotational velocity, as we used with our point cache. And I'm modifying that just so that we can have a little greater velocity on these smaller pieces. So our velocity speed, I'm using an extra velocity gain float on top of it. So whatever the velocity values are for the statue pieces, the point cache emitter, these will have a little extra added to it, so they fly a little farther. If we look at the dust emitter, this is really meant to be a bit of a trailing dust, and this is dependent again on the spawn particles from the other emitter, in this case the point cache emitter, and the particles from this dust emitter will be birthed or spawned from those particles that are the point cache particles flying with the mesh pieces. We can modify the spawn rate, that's per second, and the spawn rate per particle cap, to get a distribution that makes sense. We don't want it too heavy, but we don't want it too sparse either. These have to be CPU because the point cache emitter was CPU, but this approach can be used elsewhere with GPU particle emitters. For the dust, we're going to have a flip book of some just dust poofs, and that will be driven by the sub-UV animation module. And typically I scale the alpha down over life, in this case quite a bit, and then the scale of the sprite is done as well over the normalized age or life of the particle. So they get a little bigger as they get older. And then finally we have another emitter of dust, but this time on the impact. So this is going to receive the collision event that's being generated in this emitter from our point cache, and that'll pick up the position of where that collision occurred and spawn particles at that collision. And this is meant to be really just a local impact hit, and we don't really need a ton of these, but again we want to have some interaction with the ground. So we can have these spawn typically just one particle for each collision, and then in this case I don't do too much more extra after that with the behavior. Like the other trailing dust, I'll scale the color of the alpha really, gets scaled down, and the sprite size as well. So these share the same flipbook, so you have a continuity of look as well between the dust. Same with the color settings on the initialized particle, and again even the fading off of the alpha and the size increase. I'll add collision and drag for these impacts just because I don't want them to fall through the ground per se, but I do want them to have some impact. So now if we bring that system into our level as well as the one we created at first, we'll see these extra elements in play with the small bits of debris and some dust elements to fill out that point cache shatter. And once we have a decent look for these shapes and the behavior, we want to incorporate this particle system, this Niagara system, with the actual asset of the static mesh of that statue. So if we go back to our directory where our static meshes are and the environment, we can drag out that resource, that static mesh statue that we shattered in Houdini, and we can get a sense of like this is the statue, but the shattering of that is not connected at all with this statue. So in our next step, we'll be able to see the statue shatter into our Niagara driven pieces using some simple blueprint logic. I've created a simple blueprint to switch the visibility off of our static mesh while activating the shattering of our Niagara system. So in this way, when we simulate Alt-P, we can use a keyboard command to trigger hiding the static mesh and activating the Niagara system. So if we double click on this, we can open up and take a look at the event graph and how I put this together. The event begin play is wired into enable input and then a get player controller. From that, we're going to change the visibility of a static mesh and activate of the Niagara system. With the key input from our keyboard, we can choose any of our keys that aren't already being used by the game. In this case, we'll choose instead of right, we'll make them down, so long as they're both the same. In this way, we'll turn off the visibility and activate the Niagara system. I also created a static mesh variable, and that allows us to point to any static mesh we want, and then a Niagara variable that will allow us to point to or input any Niagara system we want. In this way, we have a blueprint template that we can use in many different ways with different systems and meshes. After we compile and save and close that out and take a look on the details, and you can see here again these variables are available, so we could switch out the Niagara system or the static mesh, and they would be useful. Let's drag another one on the level here. This one, same template, but with a simple tall pot. And with a keyboard command, we can shatter and see the results of both of these in real time. So this is a straightforward way of quickly testing the look of your Niagara system with the static mesh it was designed to shatter. In this second technique, I want to demonstrate how we can use Houdini to take a static mesh and create a shattered asset that would be difficult to achieve using the Unreal Fracture tools. I'll export this single FBX asset from Houdini to then create a geometry collection in Unreal that we can simulate with Chaos Dynamics. I'm going to show another approach to modifying a game asset so we can use it inside a chaos simulation rather than a Niagara system. So we're going to go ahead and read in this barrel game asset, and as usual we're going to need to scale that down so it's not centimeters but meters, and then we're going to jump into a subnet that I built in order to rebuild this game asset barrel into one we can shatter. So in this rig, we're going to set up a procedural arrangement in order to write out a single model that will be able to use our material fracture and shatter. And in that way, we'll be able to get the desired results from our wooden shattering to our broken iron bands we couldn't otherwise. So I'll start by clipping off the top of the model and the bottom, and then I'm going to create a line with a match size down vertically in the center. And what I want to do is take a circle and give it normals that are pointing to origin, pointing inward. And these circles are going to use an attribute wrangle to have that normal get calculated per point, with the idea that we're going to use these with the ray sop to ray them onto the model of the barrel. So we copy those circles to that line, and we have enough samples we can change that value on the points of the line to get what we think is accurate. And then we'll go ahead and jump into looking ahead at raying those onto the original model. So first we'll go ahead and modify the scale a little bit, shrink them down a little in Y with the transform. And this is just also some, we want to pick up the normal vertex attribute after we ray them on as well. So that looks like it's going to be a good profile of our original barrel. With these curves now, we can go ahead and modify, branch off and delete all but one of them. And then we'll use this circle multiple times to represent where we want to put the iron bands around the sides. So the top's in the middle. And then we merge those together. And in the same fashion, we'll use a ray sop and our newly created sides of our barrel, ray those rings onto those sides. Again, pick up the normal attribute. And then we're going to use a sweep operation with the rectangle grid to represent the actual bands themselves. I'm going to like to group these, and then we can branch off as, again, we'll take just the bottom circle this time, and we want to make the lid, or the bottom lid in this case, again with the poly extrude. So now we're starting to build this out. We have our bottom and sides and rings. We need to go ahead and make the sides have some depth, but we also want to chop them into separate pieces. So I'll build this Boolean cutter based on the size of the original barrel, modify it slightly to be bigger than our barrel, and then we'll use that as a cutter so that we are now going to chop our sides into pieces that represent what are the sides from the texture on the barrel. After that Boolean fracture, we can then go ahead and look at doing a poly extrude on each of these newly Boolean pieces and give them sides and a back to them. And in that way, we'll then be able to use these to make a convincing shattered plank of wood. We'll merge these together with our bands and the wood top and bottom. We'll reverse the normals and compute them with the facet sop, and then merge that result as well. Finally, we want to get the UVs onto our new model, and we'll do that by referencing the original game asset model, and then we'll use our labs UV transfer to transfer the original UVs onto this new topology. We also have to get a lid, so we'll take the bottom and we use our group to single that out and move it to be the top. Merge that, use a divide for any triangles we need, and then promote the normals as well. Here again, I can look at the exploded view before I do any shattering and just see if I like the number of pieces on the side, the shapes, and it's useful in a procedural way to work and preview this process before we go on to the next step. Going back up to our main level, we can now work on these parts separately, and I'll use our null SOPs to help isolate and identify each part we're going to treat separately. So we'll go toward working on our wood first, and we'll begin on the sides by blasting away the lid, which is the top and the bottom, just remaining sides. I'm going to go through a for each loop because we have a name attribute, and I want to treat each of those side planks separately in doing a material type wood type of fracture, and I'll use a cutoff set that'll use the detail attribute of what iteration in the for each loop we're in. Take that value and divide it by 10 to give a different value for each piece. In this way, we get a nice little variation from each piece getting shattered a little differently. We'll apply some normals as needed and then write this out to the disk with our file SOP there. Moving over to the lid, a similar process. We'll just keep the lid and not the sides. And even in this, we will not treat the bottom. I'm only interested in shattering the top of the lid. So the same approach, I'm going to chop this up in a way that'll be like what the texture shows us, and then I'll write that out to disk as well. Finally, the iron bands I'm going to treat differently since they're not wood. Isolate them, and I'm going to again use a match size and a grid this time to make a cutter, but like in the subnet, this would be a noisy type of a cutter instead of an organized clean one. We'll fuse the sides of the model and do a Boolean cut, just so these are split in two. We'll write those out to disk, and now we can start to merge these results together. I want to make each of these newly shattered pieces unique in the editor, so I'm going to use a name attribute with the assemble SOP. And then I'll go ahead like we've done elsewhere, put down a null, a divide for any triangles we still need, inside face UVs, a normal again if we need that, and then the important attribute create for making an inside group material instance attribute. We'll look again at our exploded view with the color for the inside and outside, just to qualify if we're happy with the look of this before we write it out. And then finally, we'll scale this up to game units and write this out as a single FBX. And in this way, we'll be able to use this in a chaos simulation as a geometry collection. Let's take a look at that next. Okay, back in Unreal, I'll import our single shattered barrel FBX. Like we've done in the past, we'll go to the source art, the shatter wood barrel directory, and bring in that FBX. Same as before with our settings for import, we'll keep the normals and we don't need to create any materials because we already have them here in this directory. With this static mesh, now we can create this into a geometry collection. The first step is bring it into a level. And then we're going to change our setting from selection mode to fracture mode. That'll open up our mode toolbar. And with the static mesh selected in the level, we can click New. And when we do that, we have a pop-up window here that wants to save our geometry collection. We have a directory already set aside for that. And importantly, we need to check the split meshes. That will allow us to take the pieces we shattered in Houdini and have them be recognized and a geo collection as separate pieces. If we use our explode mount here now, like our exploded view in Houdini, we can see those pieces that we wrote out of Houdini, that we shattered in Houdini. With it selected, we can also turn off the color by just unchecking show bone colors. And then we can shrink this back down from our exploded view. Everything is looking good. Now with the geo collection that can be simulated with the Chaos Solver, let's look at the next step of applying fields to this barrel. In our maps directory, we have barrel shattered desert level, where we will explore the settings on our master field and the geometry collection of our wooden barrel. Here, if we look at the settings for our master field, we can see we have the default sphere, and any geometry collection within that will be affected by those fields and forces. The linear and angular velocities we can play with, and by rotating, we can change the directional vector of that directional velocity. Selecting the geometry collection, typing damage, we can go in and change damage threshold, in this case making that default value much smaller so as to be more easily blasted by our master field. When we simulate, we can see the results of that master field on our wooden barrel. Now if we go in and look at our settings here on the master field, we can play around with some fine-tuning, like angular dampening. We'll keep the rotation of these pieces from getting out of control. We can also play around with the magnitude settings for the direction and the radial vector. And by doing so, we'll get a very different look to our simulation. We go to simulate. Now we have a different feel to our exploding barrel. So we have a lot of choices and options in playing around with the forces and the damage settings with our geometry collection and master fields. Next, we'll go ahead and change to a different level where we have our Roman statue FBX. That is a geometry collection as well, and another master field. So, like with the barrel example, we can play around with the position and the direction and what it encompasses of the geometry collection will alter how the sim will look. We'll see that there's some movement on the statue just from gravity affecting it at the start of that simulation. So what we want to do is stabilize that, and by going to our fields directory, we can choose an anchor field, and that will effectively make those areas within it static and not be affected by the forces. So we can position this, scale it, and place it in a way that we will hold the base of this statue from being affected by any forces, gravity or the master field. But we also have to select the geometry collection and choose to make an initialization field where we'll point to that specific anchor field. Now when we simulate, we'll see the steady base at the bottom and all the other bits getting blasted away. We'll finish out here by looking at combining our chaos destruction simulation with Niagara particles to add dust and debris. Notify events on the geo collection actor will trigger the passing of chaos destruction data to spawn our Niagara particles. Okay, now I've set up another level here for us to explore, taking our shattered geometry, our fractured meshes that we put together with the Niagara Systems and point cache data from Houdini and shattered FBX pieces out of Houdini, as well as just fractured static meshes built into geometry collections. And now we want to go ahead and run our simulation on them, but also add a Niagara component to include some dust and some extra small debris based on the actual dynamic event that Chaos is running. So to do that, we have a geometry collection already here that has been fractured, and we can use this as our guide here to build from. And one of the things we'll look at here, it's already been set up for us, is our master field and our anchor field. And if we just play this simulation, we'll see we're getting our anchor holding the statue in place, and then the master field doing our omnidirectional shatter, as well as we've added dust and debris from those shattered pieces. So I'll go through step by step now in building the setup for our geometry collection to trigger Niagara to spawn particles during the shattering event. So with our geometry collection selected, our statue here, we're going to get that back here. We're going to look at the details under the GC tab. And so if we start at the top here, what we're looking for is the events. So down here, about halfway near, actually closer to the bottom, these events will be off by default. And what we want to do is check on and notify breaks, collisions, and trailing. Each of these we will use as a chaos destruction data to feed into a Niagara system. And in our Niagara system directory here, I've already created a system for sprites on the burst or break, sprites for the trailing, and then a mesh as well for the break or the burst. So if we have these enabled during this chaos simulation, these pieces from this geometry collection will pass this data of when pieces have broken, when they first come apart, if there's going to be a collision with other objects, and while they're trailing, so after breaking, but typically before colliding with something. And each of these will have a distinct use, so I make a different system for each of these looks. So if we come over now to our Niagara setup, the first one we can look at here is our sprite burst. And I use the name Chaos in there just to remind me that this system is designed to be used with a chaos simulation. And what you need to do for this to start, for this to work, is you want to create this chaos data or chaos destruction data, and we can just find that by typing in chaos. So this parameter, the chaos destruction data, we will use in the emitter itself. When we create our particles, we're going to include a spawn from chaos in the emitter update, and then apply chaos data in the particle spawn. And in each of these, in the spawn from chaos, we're going to use that the parameter we defined for our chaos destruction data. And that'll be the path. We can then alter the parameters afterwards, but the gist of this system is when the initial burst of the simulation occurs, we want to have some falling dust. And this is going to be triggered, spawned by that event information being passed from the geometry collection. And then we're going to act on that like we have done with our other particles, where we'll apply that chaos data to the particles that are being spawned, and then we can apply our normal forces like we would with any other particle system. For this case, in the falling dust, I found that I wanted to inherit just a very slight amount of velocity, basically. And I didn't need any extra positional offset from the source of the piece itself that was being used to spawn this. And then the remainder of these modules are really similar to what I've done already, where we're applying some size over life and rotation, possibly some drag, and then a sub-U animation to play the flipbook of our dust. The other system is similar, but it's going to be trailing dust. And in this way, we're going to use a trailing dust data source, whereas in the other system, we used the breaking data. So these are the three flavors that match those definitions on the geometry collection for the type of data. So similar to the bursting sprites, we're going to again have these spawn from our destruction data. We're going to apply that in a similar way. This is going to be a similar dust, but we want it to be trailing behind the actual pieces of broken marble. So a little bit modified settings and parameters for that to achieve that look, but otherwise a very similar setup to the burst. And then finally, I always want to augment the big pieces of some kind of stone destruction with small mesh particles that represent the bits that you really don't need to simulate dynamically with chaos or shatter outside, and bring into shatter and Houdini and bring into the editor. You can augment it by having particles with some interesting mesh shapes to them. So to that, this last one will do breaking data as before, but instead of a sprite, we're going to use our mesh render. In this case, I'm only interested in just a single mesh. I don't really, you could have a little array if you chose to, but for our purposes and the size and scale I'm using these, it should be fine. Again, this is very much the same as the others. This case, I'm adding more velocity, so I want these pieces, as they're being spawned from the breaking pieces, to fling out as well. So I can add a low velocity that comes with those pieces. I can also add some curl noise as they're being spawned, so that gives it a little extra variance as they're being flung outward. And then again, just sort of playing around with the typical update modules to have their behavior look the part for what we need. So with those three defined, in the actual setup of the level, I will include those Niagara Systems. I'll bring them into the level, which is important. They need to be there where the simulation is happening. And I'll go and refine the data that we're passing. So this is our chaos destruction data. This is the same data as we were just looking at with our system here, the parameter chaos destruction data. But instead of modifying it here, because it's a parameter, I can do that on the individual actors. And that way you have a lot more flexibility to modify as needed. One system can be used multiple times with different settings. So for our sprite burst, I found that I needed to have a lot more sampling than the default. This data process frequency is running. The higher the frequency, the more it's going to try to evaluate the data of, is this piece breaking? And with that, because of the speed and the nature of the simulation, the default of 10 wasn't really producing a result that I found useful. So I played around until I got up to a value of 100 that was good. And then the maximum number of data to spawn per particles, again, was fine, just at 50. The other thing I typically change is the spawn min and max count. Again, this could be just set 1 to 1, but I wanted, in this circumstance, to have a wider range, and that gave me a better look as well. And then these other settings I didn't really need to modify. The exception is coming all the way down to position random spread magnitude. It's quite a mouthful, but we're trying to offset the position of these spawn particles so they don't all get spawned basically at the centroid of each of these pieces of breaking geometry collection. So again, experimenting around and finding these values of a min and max helped the look. For the other two, it was similar. Again, just playing with these settings to find what worked best. In this case, for a trail, I needed a lot more particles, mostly because of the distance of some of the pieces. I didn't want to have the separation of these particles and the dust associated with them to look spotty. I wanted to try to keep it contiguous, so it needed more particles in that fashion. But pretty much these other settings remained the same. I didn't really need to play around with them in the same way. And then for the mesh of the burst of the mesh particles, a similar circumstance here. I wanted a lot more particles, so I upped that max to a really large number, as well as the sampling, and then even the min max. So this one was a little bit more tricky to get the look correct. I even reduced this latency in time to be less than the default of 1. I wanted these to burst and have the same feel and energy as the pieces that were breaking. Likewise, I offset that position min and max as well. So with these settings, again, we can see I'm pretty happy with the overall look and feel. And the goal here is to find a simulation setting first, do your chaos simulation, and then once you're happy with the results of that, start to dial in each of these individually, each of these Niagara systems, to give you the look you're after and the behavior you're expecting. So now let's go ahead with this setup, and we'll introduce another geometry collection, and we can look at just applying these settings to another statue. So we're going to really just move this one out of the way, and then we'll bring this other guy over. And if you recall, we modified this geometry collection through our shattering in Houdini, and you may recall that once we have a geometry collection in our level, then we need to do a couple things to have it set up properly for the chaos fields. So this is our brand new geometry collection. What we'll want to do is go into the setup for it to have initialized fields. We want that anchor field to be used. Oops. And then because we're inside that master field, we would expect that to affect our statue as well. But now the anchor will be in place, So we can take a look at this sim. Great. So we have the sim as we'd expect. These pieces shattered like we would expect them to, but now we want to attach those Niagara Systems for the dust and the mesh debris to this actor. So if we come into here, what we're going to look to do now, if we evaluate how we set up this last one, we had to have the events triggered, checked on. So in a similar way, we're going to go down to our events under all, or even in Geometry Collection tab. And we want to set that notify breaks, collisions, and trailing. And with that, we can go back into our level, play simulate. So now again, we have our trailing dust, we have our burst dust, and we have our debris flinging out. In closing, my goal in this masterclass was to demonstrate the benefits of using Houdini to provide a procedural approach to create fracturing static mesh geometry that, coupled with point cache data, provides a flexible approach to use in Unreal for both Niagara Systems and chaos-driven simulations. Looking ahead, there is an opportunity for building these Houdini networks into HDAs, incorporating these HDAs as engine plugins inside of Unreal for procedural geo-collection creation for use with chaos. There is also an opportunity to create a procedural fracturing system inside of Unreal 5.5 using data flow graphs that will allow even more flexibility working with the techniques I've shown today. Further information is available at epicgames.com under the Developers category for chaos and data flow graphs, as well as Side Effects Houdini Engine for Unreal plugin available at GitHub. Finally, I want to thank the host of Everything Procedural Conference for this opportunity to share some of this knowledge with you all, and hope you find clever ways to use it for your VFX destruction.